Day 2, correct. So again, yesterday was just a quick conceptual intro, guys. Today we're going to start the math stuff here. Okay? We're going to start looking at terms like density, pressure, volume, mass. Okay? Remember I said yesterday I was just talking about what fluids in general were. That was more like conceptual stuff. Today we're going to start looking at some mathematics. Well, guys, the hard part is this. You can't do whatever you're doing, stop, and focus up here, please. Whatever you do here for this kind of topic, you can't actually make any conclusions without mathematical evidence. We could say stuff, and we can come up with ideas, but all of those ideas, even the stuff I said yesterday, was all based on math. So just thinking about it alone is not going to be enough. Okay, again, we have to make sure that for this kind of a concept, we understand where it's coming from. Now, the first and most important thing about a fluid is its density. The density incurs so much. Any formula you're going to use for fluids, you're going to use the density of the fluid itself. So before we start, let's talk about density. Where did we recently talk about the term density? And we specifically used it to represent something. Pressure. Pressure, okay.
The water.
And under the water, but we didn't talk about density there. Black holes. Dark holes. Black holes. In the black hole example, we said, imagine if you took like the Earth. Remember the example of class? I said if you took the Earth and crushed it into the size like a tennis ball. You know? Or you took, and that was actually in the video that was on there also. They talk about that as well. So it gets super, super dense, which causes a very strong gravitational attraction. So density is really how compact an object is. So let's start with density.
Nice.
I know, I do.
Oh, really?
That's all it is.
Yeah. I was like, whoa. I saw you. You saw me, I was like, hey, you're laid out.
Okay, that's all it is. How close the atoms are to one another. So, how compact is it? Okay? And again, you do not need to write my definition out. But if you don't know this, if you don't understand what atoms are in atom structure from something like maybe chemistry, then you might want to write that down. Because density has to do with how close the atoms are. You can have lattice structures, you can have hexagonal structures. The structures change depending on your bonds. If you have a polyatomic ion, if you have a hydrogen bond, okay, if you have an alcohol bond like an OH bond, there are different kinds of bonds. Those are dictating the angles. If the angles are obtuse, acute, that all has to do with how close they are. The whole study is called materials science. Materials science itself is an entire field that studies atomic level particles. Now, you use chemistry, you use physics, you use engineering, any of that stuff you're going to use in materials science. Absolutely. Okay? You have density of an object, but once it gets heated up, the object starts to what? Move rapidly and expand. So its density will naturally or generally, not for all things, let's say generally right now, decrease generally as you heat up. So the example we'll start with is exactly what Kenny just said. Let's say, for example, here, you go in your freezer, okay, you put a can of soda in there. Is that a good idea?
No.
It expands. Because when ice freezes, or when water freezes to become ice, it expands. Well, the molecules are realigning when they're becoming a solid. That is one of the few examples where a solid is less dense than the liquid. That's hard to think about.
In between?
Think about it this way. If I had a, say, basin or a pool, a little like a cup holder of liquid gold. Okay, liquid gold. It weighs a certain amount. Now, when it solidifies, its mass hasn't changed, so the weight has not changed at all. But when it solidifies, the molecules get closer together to realign and they become a solid. Generally speaking, gas molecules, you see gases, whenever you represent a gas, you show like some sort of a space, and you show the molecules really far apart, like randomly running around or flying around. When you see a liquid, you see that it's in some sort of a container maybe, and the molecules are a little bit closer, but they're still kind of spread out. And then when you see the solid, what do you usually see?
It's a shape and they're all like.
But you see like the lattice structure usually. You always see like you see some sort of a lattice along the entire way. Lattice just means like a matrix, if you think of it that way. A matrix of rows and columns. The molecules get closer usually. So if you have liquid and then you make it a solid, traditionally it gets more dense or more compact. But ice or water is one of the very few exceptions because of the hydrogen bond. When the hydrogen bond becomes a solid, its angle actually changes. The angle between the HOH bond, that's what it is. Okay? It's an HOH bond. And it actually changes the actual angle. And we did this last year. And I know a lot of you got to think back, or 2 years if you did this summer. There was an example where I taught you guys law of cosines and law of sines. And in the law of cosines example, I'll bring it up right now so you can see it. In the law of cosine examples, we looked at an actual H2O molecule, and we looked at the angles between them. And what you're going to notice, if I can find it quickly, it was a classwork assignment toward the end of the year. So it's probably 76. All right, thanks. Here it is. So this was the example we did in Algebra 2. We did this in the summer, and then last year if you had me also. So for this one, we did it. It was a worksheet that we did. We used law of cosines to find the angle here, to find the angle here. Trust me, I know I did. It was one of the things I did in every class. So what you're going to notice, though, is this. The whole problem here is to solve for the HOH angle. Here's H, here's O, here's H. That's the HOH bond. This here is the angle. What happens, it turns out, which is very rare, is that the angle becomes more obtuse. It's a certain value. Hypothetically, let's say the angle is 105 here. It might be 107 here. That change in the obtuse angle makes the object expand more, which gives it more volume. But it's got the same mass still. The object hasn't changed, but it's got more volume now. So it must be less dense, which is a very rare exception to our law. Again, when you go from liquid to solid, traditionally it gets more dense. This, the density here goes down. Okay, so these are just examples of density. Now, let's go back and actually define density mathematically. Many of you know this. Density equals, what does density equal to? Mass over volume. Density, now, you guys have learned density as capital D. You're going to hear it, it's called rho. It looks like a P, but it's not. Again, watch how I'm drawing this, please. You just roll like that. You're just looping. You don't have to, no, there's no need to make like, there's no need to go like this and come back around. You're literally just looping around. Just loop around. That's all rho is. Rho is equal to, as we all just said, mass over volume. Okay?
Any other complicated sign and data?
No, not really. Rho is the only one. How do you spell rho, anybody?
R-O-W.
R-O-W-E.
What is it? There it is. R-H-O. It's one that nobody really knows, that one. Okay, it's just a Greek symbol. That's all it is.
Because Edgar has a laptop. Right.
No, he didn't look. He was looking up here the whole time. He tried with R-O first. I heard R-O-E. I heard R-O-W.
What's the reason why they use rho instead of using
D?
Yeah, is D used for something else?
This was just used traditionally. It was traditionally used. If I saw capital D, I would think of, not really. I would think of distance before displacement, because displacement is x, remember, or position, or y. I would think of distance. What else? There's probably a lot of electrical engineering application for D that I don't know of, to be completely honest with you. Maybe a reason, but rho has been used for a long time. There might be in your book, it might say why. A lot of times they put a little, excerpt of who discovered it. So if you want to look, check. Yes. So, let's start analyzing. What are the units going to be? You should know this, guys. What are the units of mass?
kg over grams.
Units of mass are kg.
Over second. No, whatever.
Well, traditionally it's just meters cubed, but in our case, here's what we're going to look at, just so you guys know. We are going to look at, which is very odd to say. We're going to look at this, though. We're going to use this as our units because it's more reasonable, and I'll discuss why. Numbers like kg per meter cubed don't actually make much sense. Okay? That's I'm telling you the standard units, and I'm showing you what you're going to use. Standard units for mass is kg, and for volume is meters. We're not going to use that though.
So massive. Grams over centimeters.
So,
Again, guys, a lot of things are going to be given like this. A lot of them will be given like this. If you need to use the formula and you want to convert to standard, please convert when you're doing a math. But this is how you're going to see them given a lot of the time. Just so you have an idea. Okay, just so you have an idea.
So your answer is always going to be grams.
The problems a lot of the time give you units of this.
Okay.
To do the math, though, you need this. So I'm trying to show you that you'll be given this because it's always given this way. Because of the fact that I'll explain why in a minute has to do with water, and there's a reason for it. But here, this is what you're going to use mathematically. Now, converting from here to here is not easy. You're not just converting centimeters. You're converting centimeters cubed. So my recommendation to you right now, I can go over it, but there is a unit converter in your calculator. Feel free to use it for now. Okay, it's a matter of moving zeros. That's all it is, really. You're moving a decimal. Okay? If you need help, please ask me. That's fine. But you can use the unit converter on there. It's under apps. Feel free to look at apps and look for densities. Okay? For this example, let's start by looking what happens to the function as we change values. So, let's go back to the water example. What happens again when you put water in the freezer? It expands. Yes, it freezes. It expands. So what happens to the volume if it expands?
It increases.
So we see that if the volume goes up,
the
density has to go
Up.
down. It's in the denominator. Remember, it's inverse. Inverse. If the volume goes up of an object, but the mass remains the same, like water, the volume went up. But the mass is the same, it's the same amount of water you put in there. If the volume goes up, the density must go down.
So the mass goes up.
If m is constant, okay, you might want to write that down also. If m is constant, m is not changing. So you put the same amount of water in the freezer, you get the same amount of water out, it just happens to be frozen. So the mass has not changed, but the volume clearly went up because the mass expanded. But now that means the density must have gone down. Doubtful first.
So you said the velocity goes up.
Volume.
Volume. Sorry.
It's okay.
I said the volume goes up. What was it on the other arrow where it goes down? Like, what is the P stand for again, or what is it?
Density.
Okay. Thank you.
Elizabeth.
Underwear apps.
Side tools.
This is just like
Underwear on the app, not underwear.
Underwear.
You said underwear. You did.
Underwear.
Wow.
Let's see if there is one for that.
If the volume goes up, the density goes down. Okay? So, what happens if I have a solution of water?
Yeah, we were trying.
Okay? I've got water in a beaker. Let's do a hypothetical now.
Yeah, I did.
I'm sorry. Why don't
Okay, I've got water in a beaker. And you've all done this before in chemistry.
No,
Okay.
you didn't.
You've done at least this. Even if you've done this at home. You put sugar in water. What happens to the sugar? It dissolves, right? So let's talk for a second. We're not talking about molarity. We're not talking about solid solution, supersaturated. We could talk about it another time. For now, the density. This has a mass. Okay, it has a mass of water. And then I take sugar, a sugar cube, for example. God bless you. And I take the sugar and I put it in. Over time, the sugar will definitely dissolve, especially if you stir it, right?
Right.
Especially with hot water, it will dissolve instantly.
Right.
So, tell me something. I added mass, but has my volume really changed?
No.
No, it hasn't. So what have I really done to the solution?
Nothing.
Again, density equals mass over volume. I've added more mass. Now I have, instead of mass, I have mass of the water plus the mass of the sugar. But there's no real change in my volume. So what happened to the density? It increased. Be careful. Again, think about it this way. If I have this Activia container, and I didn't even mean for that though. The Activity container holds a certain amount of yogurt, correct? It's got a volume, a capacity of its volume. I'm gonna keep eating it. So right now it's like maybe a third full. If the whole thing was filled, the overall container would have a certain density. But as I eat more of this, the mass goes down. The mass goes down. So I get denser.
That's a smart way of thinking.
Well, not necessarily, because my volume will go up too. Yeah, your volume will go up also, so you might not get denser, you get heavier. Now, oh, please don't stop. James, no. We're going to get this changed. So, if we started with a full container, it's got a density. It's got a density because its mass is some value and it's got a volume. But now the mass went down for this example. So if the mass went down and the volume is still the same amount of volume here, the overall density of this overall container, the whole container, has definitely gone down. Because the volume is still the same of the whole container, not the yogurt, the container. Okay? So if the volume stayed constant and the mass went down, the density goes down. But in this example, the mass gets added, doesn't it? So the mass went up. So if the volume is constant, and for example, the mass went up, then the density must go up. Again, the volume is the same, but somehow I'm adding more mass to it. I'm adding more and more mass. So its density must go up. Okay, its density must go up. If the volume is constant and the mass goes up, then the density must go up. Okay, V is volume, and V is volume in this case. Lowercase v is velocity. So we got the mass of the water initially over the volume. So we have overall density. But then suddenly we add the sugar cube. But it doesn't change our volume. So we must have an increased density. Not by really anything at all. You don't notice it, right? It's barely anything. Okay? But again, you'll see that it does go up. Just like the example of the container. The overall container's density must go down if I take mass out of it. I keep being good. So, back to the question of grams per cubic centimeter and where it comes from. Turns out that water has a density of approximately 1 if the units are grams per cubic centimeter. If it's not, and I shouldn't put GM, sorry, grams per cubic centimeter, okay, is about 1. Now, if I look at the value in kilograms per cubic meter for water, and again, this is water, by the way, this is not ice, but water at a certain temperature. I'll explain that also. If we look at in kilograms, it happens to be 1,000 kilograms per meter cubed. Just so you know, so you have an idea. Okay, so when you're given things in grams per cubic centimeter, if you want to go back to here, what do I have to just multiply by? 1,000. If you want to write that one down, it might be worthwhile. To go from grams per cubic centimeter to this, you multiply by 1,000. And it all comes back to the unit and dimensional analysis. Write that down and just observe what I'm about to write on the board. You do not need to write this down. If you want to show where it comes from. But notice, you're multiplying by 1,000. Here's where it comes from, because I know a lot of you are interested in this stuff. If I have kg, well, I want to go from grams first. Let's start with grams. I've got grams per cubic centimeter. I want to convert grams. I say to myself, okay, I know that there are a certain amount of grams per kilogram. There are 1,000 grams. Oops. 1,000 grams. Thank you. Oh my gosh. Per kilogram. What happens to my grams? Good. So now I'm in kilograms. The tricky part is the next part. And it kind of is a little bit weird. Because you're going from centimeters to meters. What's the conversion? How many centimeters are in a meter? 100 centimeters. But it's cubed, isn't it? So I need to say that there are 100 centimeters per meter. But how many times do I have to do this?
3 times.
3 times. So either I can cube the whole thing, or just I can write it out 3 times also. Okay, it's the same thing really. And now, only now can I cancel the cubic centimeter with all 3 of these centimeters. And I'm left with how many meters cubed? MMM cubed. So here, 100 times 100 times 100 is 100,000. Okay, I'm going to say, oh no, sorry, a million in this case. Look at the amount of zeros. Count your zeros. How many are there total? 6. So you get 6 zeros over. So when I simplify this, 3 zeros cancel with 3 zeros. There's your 1,000 from before. Okay, that's the dimensional analysis. That's why I said if you'd like to use your calculator, that's fine. Or just remember to go from grams per cubic centimeter to kilograms per cubic meter multiplied by 1,000. That's where the factor comes from. Because when you convert this, you get 1,000 as your answer. Where does that come from? Cancel your zeros with those 3 zeros. All right. So water happened to have this density of 1, which is very, very convenient, by the way. Very convenient. If it didn't, a lot of our laws, a lot of our daily routines would not be true. For example, people, and you don't even think about this kind of stuff. When your washer runs a load of water, especially the new washers with a lot of electronic stuff, they're always sensing mass and weight. They're also using the density of water in their calculations. It happens all the time. They have to incorporate the fact that you have detergent now, so your density has changed. Okay, all these things are taken into account in those programs. Another example, and this is just a general application, any sort of food processes. So if you're cooking food and you're using oil, and you put oil in with water, but you notice what happens to the oil?
Yeah.
It comes to the top of the surface, because oil is less dense than water. But I am more dense than water, so if I jump in a pool, what am I going to do?
Float.
No.
You're gonna
If
sink.
I just jump in, I will sink, actually. If I take in a lot of air before I jump in, I might float. That's the weird part. Try this sometime, guys. If you're ever in a pool, take a deep breath, and try to go to the bottom of the shallow end, even the shallow end. It won't work. You're going to float back up. What do?
You gotta blow it all out.
Blow all the air out, because now your volume has gone down. Your volume has gone down. See that? So if your volume goes down, your density goes up. That's why you sink to the bottom. Go back to the example. Okay? You take in all this air. So I take a deep breath. So my volume goes up a lot, doesn't it? Take a breath, you feel your chest rise, your volume goes up, your diaphragm expands. So, if you breathe in, your volume goes up. We said a minute ago, if your volume goes up, though, your density goes down. Your density goes down. Therefore, you float. Okay? This is conceptual stuff again. If you... I gotta fix that. If you breathe all the air out, what happens to your volume? It decreases. Breathe everything out. Everybody just go. You'll feel yourself pull over, right? But breathe everything in. You'll feel your chest rise. You'll feel your expansion of your lungs. Okay, so your volume goes down. Thus, your density goes up. So you sink. Okay, and I'm telling you guys, try it sometime. Breathe everything out and just go to the lower end of the pool, not the deep end. Go to the low end and try and go to the bottom, and you'll feel yourself stay down. It works in the deep end too, but just be safe. Okay, I'm gonna hear that somebody drowned. That's what I mean. He said not to breathe. He said don't breathe. It'll work. That's not what I said. Yeah. Don't try this at home. Try it, but try in the shallow one, please. All right. So, with that said, it's very important to know. It's very important to know if something is more or less dense than water. Water is our benchmark. So if you're comparing stuff, it's a standard to compare against, or it's a control group. Okay? When you do experiments, you have control groups, something that's unchanging. Traditionally, we measure the density of something against water. That's usually something that's good to measure against. Now, if you're cooking food, I use the example of oil. If any of, let's say, that's another good example. All right, when you're 21, you might, decide to drink beer one point in your life. Okay? Now, if you ever look into the way beer is brewed, they use something called mass density and specific density. And what it is it's the ratio of the density of the actual alcohol to the density of water. So say the density of the actual alcohol that they make is 2. grams per cubic centimeter. Then the ratio is just 2 to 1. It's always something to 1, something to 1. So they use that there. What else? A boat. For a boat to float, density is used all the time. I mean, the shape of the boat is really the key point, because the boat's density is more than water. Please, go to the beach sometime. Find a piece of, like, I don't know, scrap metal or something you don't care about. Throw it in the water. What's going to happen? Not in the water like that. You're going to pick it up after. Relax. And when you throw it in the water, what happens to you guys? Come on, go with the example, please. Go with the example. I know, really. It's like worst lesson ever for that kind of stuff. If you take it the wrong way. You put something in the water that's metal, it sinks. But think about a boat, guys. Boats have a lot of metal. They are fiberglass also, but they're a lot of metal. The shape of it is really what keeps it up. But it has an overall density, because look at a boat. Here's the shape of the boat, right? Say it's in the water. Part of it's under the water, part of it's above the water. It has a density. Its density is the whole volume over the whole mass. Well, that becomes a little bit more complicated when you look at these, abstract shapes. Okay, and depending on how low in the water it is, how above the water it is. Okay, so depending on it, it's going to change. But just keep that in mind, density does play a major role. Now, another application of density. Another one. Imagine you had a water gun, and you're in the backyard. Okay? And you're with your siblings or friends, whoever it may be. Okay? Or sure, okay, you do imaginary friends, those two. So you have a water gun, and you're squirting somebody, right? How does it work? You pump it up, it gets a pressure, and then you shoot it, it shoots. Now, you're not going to actually try this, but imagine, if you will, fill the water gun with something that's very, very dense, not water. So, like, imagine something like
honey,
molasses, which is also viscous. That's what molasses. But molasses or honey, those happen to be. Those happen to be very what's called viscous, actually. And viscous just means it doesn't want to flow smoothly. And try syrup or try honey, pour it. You know, it takes a little while for it to drip over the edge, and it flows very slowly. That's because it's viscous. Viscous. But it also happens to be dense. If you tried to shoot that out of the gun, it wouldn't work too well. I mean, you might go like, a few inches out of the gun. That's why you put it in the balloons. Okay? So the idea of density, it always occurs in stuff. Let's go into an example where we can see this now. Okay, let's look at an example of this.
I don't know, I think 3D, right?
I want to see it.
Say again?
No, it's Italian. Can we come at that again?
It's coming out again.
Who cares? I just can't make it.
DiCaprio was like gangster in that movie. He takes the rich girl away from the rich guy.
I can't believe he's like, oh, I'm not too long.
He draws her. I'm gonna say how. He draws her. That's a thought.
It's gonna get a big head.
If
$100 million on his head.
He's right.
How about salt water? Is it still one?
No. All different. Salt water, guys. Salt water is less than one, actually. No. Sorry. Salt water is more than one. Hence, that's why you can really float at the beach very easily. It's more than one, so your body's able to be less dense, so you stay above the water. Yeah. The volume of an object, a balloon, for example, is triple. Assume the mass is held constant, which is a fine assumption because you're just increasing air. Air has almost no mass. The mass is very small. So if you just keep pumping helium into it or air, it's not going to really change the mass.
I wonder why that is.
You know why? You know when you like suck in your ear, your voice just gets more high pitched. You know
Why is that?
Why does that happen?
Yeah.
I don't know, actually. Not sure how it reacts.
Google.
Look it up, yeah. Look it up.
Actually, be right.
It's called,
Yeah, let's throw
it's probably like on just that, you know how he's supposed to be like, look it up?
That's what I was thinking. He always says, I'll look at mine. You look at it.
I know, I look up a lot of stuff, and I should start telling you guys to look more of it up, and Mrs. Smith does that. I know, I gotta start doing it. So, we got a balloon. Let's say the balloon is, approximately spherical, not, balloons in weird shapes. Let's say it's an ellipsoid or sphere for general. Now, I take the volume, God bless you, I take the volume and I increase it a lot. I increase the volume a lot. But the mass is approximately the same still. So the mass is approximately the same. The overall, because the mass of the balloon is still the same rubber, right? You just add more air to it. But the general mass is about the same.
Density over 3.
Okay? If I look here and I say, well, it's just mass over volume, isn't it? Isn't that my formula there?
Yeah.
So if that's my formula, and my new equation now, in my new equation, what should I do? Raise your hand, tell me, what should I do for my new equations, for the new density I want to calculate? Sorry? For the new equation, what have I done to this problem? Very good. So I've tripled the volume, haven't I? Isn't that what's going on right there?
Yeah.
I started with mass over volume, but now I have the same mass, but now it's over triple the volume. Triple the volume. So really, what this means, what this really means, is like having a 1/3 in front of the MV. And that's the weird part to remember. If you still have the MV there, it's like having a 1 here. Isn't there really a 1 here? So isn't this really like a 1/3?
Yeah.
So what are you doing to the density? You're multiplying by 1/3,
Divide by 3.
or you're
Divided by 3.
dividing by 3. So what happens to the density of this object? If it continues to go up in volume, it goes down. The density goes down. By what factor? So let's write this out. Density goes down by a factor of 3.
This is saying.
So either tell me one of two things. Tell me the volume was cut in thirds. I'm sorry, not the volume, density. Either say the density was cut in thirds, or you could say you have 1/3 of the density. Cut in thirds is division, 1/3 of the density is the multiplication part. So either say the density has been divided by 3 or multiplied by 1/3. Okay? That's another way of saying the density has gone down by a factor of 3. What I said here, and by saying it's divided by 3 or multiplied by 1/3, those are synonymous. They are all the same thing. Are we kind of clear on what density is? It's a very important thing. And I know you learn about it in physical science, but you don't always go into what its maybe real-life applications could be. Okay? And there's a lot of applications of this. You use it all the time. Sorry.
I feel like Sonic and Pecker.
What about the volume? The volume is the amount of space taken up. The mass is the amount of matter. The density is the amount of matter per space. Matter, mass, per volume, per space. So it's how compact it is. Whereas volume, I mean, sure, if it's compact more, it's less volume. But if you compact something more, isn't it more density actually? So that's why they're inversely related to each other. Inverse relationship. So as the volume goes up, its volume goes up, but the density goes down. Sure, the volume you can see, whereas the density you have to determine by figuring out the mass by mass weighing out mass, and then figuring out the volume by either squaring it or graduating cylinder. Okay? Alright, quick stuff. First, if you have me for calculus, this should be automatic because we do it all the time. Volume of a prism?
Base times height times width.
Thank you, and he's not even in there. LWH, or base times height times width. Okay. That should be off the tip of your tongue, not 10 times off the tip. Okay. Now, I know a lot of you know this. Hold off for a second. Here's my example I gave last year also. Imagine if you have a coaster. A coaster that you put on your table so you don't get a ring from the drink. Imagine now if you take a coaster and stack it up, stack 10 coasters that are identical, you're going to end up getting this shape right here. Okay? So what you're really doing, I know you're discussing, but I can't hear myself over there, okay? What you're doing is you're taking a coaster and you're stacking it up. We call the stack up the height, don't we?
Yeah.
That's the height. So that's all it is. The area of the base, which is a coaster, that's a circle's area really, times the height. Same thing goes for this problem. LW is really the area of the base. And there's the height up top. Again, remember, LW is really the area of that base at the bottom.
So you do a curriculum,
Can I do a what? Yes. Okay, LW times H. Thank you. Now, the only one that's a little bit odd is a sphere. Okay, because a sphere does not follow extrusion. This is called extrusion. Before I get to a sphere, let's talk about extrusion, what it is.
it's like the expanding of.
The expanding of something, good? Yeah, of two what kind of surfaces? What are they? Flat, and what do we call them if they're flat like this?
Horizontal, perpendicular, parallel.
Parallel. Okay,
Oh, yeah.
so remember, a prism is defined as a base, the same exact base, and they're connected. So this is a prism, up and down, it's a prism. This is a prism, up and down, left and right, front to back, either way. Now, here's where extrusion processes come about. Imagine if you had like Gumby. Everybody know what Gumby is or no?
No.
Oh,
Yeah.
You don't know what Gumby is?
It's
Okay.
a piece of gum. Like a jobber?
Wait, the cartoon?
Yeah, the cartoon, right?
Gumby looks kind of like a gingerbread man.
Oh, yeah.
Okay? It's a green and it's a rubber material.
Yeah.
And you can stretch it, you can move it around, it's a toy when you're a kid. Now,
Everybody's like,
clearly,
Yeah, I'm trying for that in the measure.
Your childhood.
come on, it's 10 seconds, so about Gumby. Let's get back. Clearly, Gumby has a third dimension. You can hold it, right? So it has some sort of a depth. It's got a depth in all directions, okay? It goes back in every direction. It's got a depth to the leg there. It's got a depth over here. So we can see Gumby goes back. Now, a lot of things that are made out of rubber or plastic, they make what's called, well, Taser, what is it called for drawing? A stencil? When you like highlight it, a stencil? Okay, so we'll call it a stencil for now. Forget the actual word. I think it's a stencil actually. A mold or a stencil, mold is a good word.
It's stencil.
So, imagine you have a stencil or a mold, and the mold was the shape of Gumby. And you were able to take rubber, melt it down or soften enough that it can be malleable or formed. Malleable means formed. So if you take that rubber and push it through, you push it through the actual mold, and you push it through maybe like an inch. Gumby is now an inch thick. And then you cut it off on the other side, you got Gumby. Is that clear?
Yeah.
That's what extrusion is. It's taking some sort of material and either pushing it through a mold or pulling it through to get another shape. So another example is if you had like really, and you can do this, I studied this for a long time because it's what's called manufacturing, which if you want to do engineering, you want to make some money, manufacturing is like the field to be in, okay? In manufacturing, you learn how things are created.
Discovery.
If you push them through too fast, it'll come through and pour through as a liquid. But if you push it through very slowly, it has time to solidify, especially if you have a coolant running over it. So imagine you have chilled air running over the end of the mold in this warm mold in the inside.
Isn't that
And
how
the
they do
warmness
light
is
bulbs?
coming through. So Gumby is slowly coming through here. It's going to fall apart if you don't cool it instantly. And so you'll run cold air over it and push it through very slowly so that it solidifies when it comes through.
Isn't it?
If you think about an example, there are many examples. Anything that can be formed into like liquid is really is a mold.
So I have a night guard.
A light guard?
Night guard.
Night guard.
For your mouth.
Yeah, that's a mold.
Yeah, I put it in a bowl with water. Then you let it cool and you put it in your mouth and bite it as hard as you can.
And it molds to your shape of your teeth, and then what do you do every night?
I put it.
I have the same exact thing, James. I have a night guard as well. A lot of people have TMJ or grinding. I have grinding, which is really bad.
You too?
You grind your teeth at night. Like if you heard the sound of the teeth grinding at night, it's insane how loud it is. You can hear it from like the next room. Like even when I was younger, my mom used to be like, "You're grinding again. Relax." Like you got to relax before you go to bed. If you have a lot of thoughts going on and you're very stressed, a lot of time you grind. I grind a lot. So you get what's called a night guard. You put it over your teeth so that when you grind, you're grinding on the plastic and it's not your teeth. Because ivory grinding on ivory eventually will wear down. But the plastic itself means you're just wearing down the plastic. Because the hardness level of ivory is greater than the hardness level of plastic. So that is another example of a mold. That doesn't happen to be extrusion, but it's a mold. It's exactly what extrusion turns out to be.
What about something like retainers?
Like a what?
Retainers.
Retainers? Do they mold it? Do they fit it to your shape to the roof of your mouth or no? Same thing, it's a mold. It's not extrusion though, remember. Extrusion is taking a shape and pulling it through the opening.
A light bulb?
You're pulling it through the opening. So,
Light bulbs, aren't they made like that?
I don't know how a light bulb is made. It's possible. If you could look it up and send me a link or something, write that one down too. Look up how a light bulb is made. Guys, look up this stuff if you're wondering, and please share it with me so others know too. A good example, oh, here's a great example. Before we had these really intricate ways of making baseball bats, not wooden. Wooden baseball bats are made on a lathe. They take a block of wood, they put the skin, and you see it, and it cuts in. How it's made is a very good example.
And then they sandwich.
For metal, though, for a long time, here's what a metal bat used to be. It would be a metal casing, and then just air inside of it. It was literally a metal case. It was a metal solid with an end cap on the end of it. Well, how did they do it? Here's how they did it. They took, instead of a stencil, they took a stencil like this.
How did you do?
So inside of this cavity was liquid metal. So you have all this liquid metal filled up. And there's an opening. Now, this opening here needs to be fixed. So this is not like just floating in midair. This is a metal rod that's already there, and the metal rod extends back. So when they push, they have a pusher on the end, and it's actually what it's called. They have a pusher here. When they push it to close, and the top is all sealed off, the top is sealed, when they push the pusher in, some liquid has to come out, doesn't it? If you're like taking a toothpaste, and you push down on a toothpaste, where is it going to go? It's got to come out. Nowhere else for it to go. So it comes out here. Now, if they do it in a slow enough process, they get this metal cylinder that has a hollow inside. And then they put a cap on the end of it, and there's a baseball bat. Now, you wonder how did they get the contoured shape maybe? Well, they can have a variable function. This is a variable cross-section, and it shrinks and expands to give you that contoured shape to it. Okay? And that's a little bit different. It's a lot more intricate. But generally speaking, pull metal through, you get this metal shell, put a cap on the end of it, you got a baseball bat. Okay, that's how general stuff is made. Again, there are a lot more intricate processes than this, but this is a good example of where it's going to come into play. Where does this come from again, though? Remember density. Okay, remember the density here. The density of the object will affect the shape it takes. Okay?
Don't they put corks in aluminum bats?
Do they put corks?
No, don't they?
No, the term corking a bat is not actually that necessarily. Corking a bat has to do with changing the overall weight or density of it. For a long time, the material, which is called cork, which is like the top of a wine bottle, that's what cork is made of, it's actual cork. That's what they used for a long time to change it, to give you more of a distance. That's what corking a bat is because of that. Now, there are many ways to cork a bat that does not involve that. A lot of bats for a long time, they called, when I was a kid, the bat, I remember the name of the bat. It was it was the red line, and the end of the bat had all these little BBs in it. There were little BBs. You know what a BB is? Little metal BBs, little ball bearings.
Oh, yeah.
Little metal, like the magnets I have that everybody throws, but not magnetic. Imagine all those in like a container, and they put them at the end of the bat, and they called it the mother load bat. That's what it was called. And it was really corking a bat, even though it's not the same thing. You're giving more power in an illegal way. And they banned the bats after a little while. They realized that it was not, because off of those bats, a lot of pitchers were getting injured. Because you can hit it so fast because it was cork that pitchers didn't have enough time to react. And they would get line drives hit back, and then they would get injured. So they actually took them off. That's why, by the way, in baseball and sports, they changed rules. They've changed the stitching on it. The tightness has changed over time because pitchers were getting injured. Because they had the stitches used to be really loose, so a lot of home runs were not hit. Then they tightened the stitches too much, so they had a lot more home runs. Then they had to loosen them again because pitchers kept getting injured from it. Because it's physically impossible to react at the time. Okay, again, changing that. But yes, these are all other applications. For an example, let's do one more example in the day for density. Okay, before we go to pressure tomorrow, we'll start talking about pressure. Guys, I'm going into a lot of detail about this stuff because I want you to see where it's actually used instead of just math. And I try to do that as much as possible. This happens to be a good example of it. So remember, I know we didn't do a ton of math there, but the relationships are what you want to know. As the volume goes up, the density goes down because they're inversely related. Okay? As the mass went up before, the density went up. Because if you keep adding mass to something, its density will go up if the volume doesn't change. Let's look at an example of... Where's the example I wanted before?
It's on page 532.
Oh, here we go. Here's the example. Sorry. So, a minute ago, we looked at a prism, LWH. We looked at a cylinder, pi r squared h. We know the volume formula. But what about this? And this is something you want to think about. And some of you might know the answer already, but think for a second. We know the density of wood. We know the density of certain rocks. So, for example, slate has a certain density, or copper for the metal has a certain density. It's not always given in a shape of a rectangular prism. So what if I picked up a rock on the ground and it was cobblestone? Cobblestone is a combination, but the word is conglomeration. It's a conglomerate. Because it is a word. It's a bunch of different rocks put together. So say I picked out one of those rocks, and I have this odd-looking shaped rock. And I ask you, tell me what the density of this rock is by finding its mass and its volume. Because remember, density is equal to mass over volume. Okay, so if I want to find the mass, anybody remember what I used for the mass?
Yeah.
Grams. So what kind of an object should I use to measure mass? A scale, good. But remember, not a scale that measures weight, but measures mass. So maybe like a triple beam balance. We've used those before at some point. It's a balance on each side, the one where you move the little weight across and it measures the mass. Or there are digital scales next door in the chemistry room now. There's a little metal pad, but the object you measure in grams. So that's fine, so use a scale. Great. What about volume though? Okay, imagine you couldn't melt, if you couldn't melt it down or anything like that, you couldn't change its shape. You cannot alter the shape.
Laser.
What is it? Displacement. Whose principle is that? Come on. No? Big dude. He was big. That's how he figured it out. He got in the tub.
Oh,
the
the
water
tap.
flowed.
No, the tap.
No, that's the president. He happened to have that also. He died in the tub. Didn't he die in the tub or something like that? Yeah.
You got stuck.
He got stuck. Who came up with the principle?
So now it's a king.
Batman. It had to do with King Harry's crown later on. He used this guy to help him with King Harry's crown.
Oh.
Isaac?
It starts with an A.
Hagrid? Oh,
Albert.
Albert Einstein, Da Vinci,
Aristotle.
Ooh.
Michelangelo.
Arthur.
Archimedes.
Archimedes. There it is. Archimedes is a big guy. Archimedes' principle came about. He got in the tub one time and noticed what happens to the water when you get in the tub. It rises, doesn't it? It goes up. His happened to go out, so he wasn't able to do the experiment that time. But displacement. So imagine now you have a graduated cylinder. You've done this, obviously. 5 milliliters, 10 milliliters, 15 milliliters. Now, you start by having the water level at 10. And how do you measure? What do you measure? The what? What is that called?
Meniscus.
What is it? Meniscus. So the water level, it's part of your, it's a tendon, I think. Tendon? Or I don't think it's a bone. Anyway, hold on, I'm running out of time. So the meniscus is the bottom of the curve, remember, because it has, like adhesion or cohesion.
Yeah.
Adhesion in this case. Adhesion is two separate surfaces, water and plastic. Now, if I drop the rock in, the water level might rise to that. So what's my displacement? How far did it go up? 5 milliliters. So the volume is 5 milliliters. Well, what did I tell you guys? We use cubic centimeters, don't we?
Yeah.
A milliliter and a cubic centimeter are identical, it turns out.
What?
That's one of the other things. A milliliter, again, the volume of this object went up when I plugged it in here, and we got 5 milliliters for the volume. So this is measured using displacement. Well, if I want to know, measured using displacement, if I want to know what that is in volume or in density in my standard units, I'm going to have a mass in grams. Let's say we measure the rock, it turned out to be 10 grams. We got the milliliters as 5 milliliters. A milliliter is the same as a cubic centimeter. So you can also write it like this. It turns out to be one of our awesome conversions because of the metric system. Not the English system, but the metric system.
Yeah, it's English.
Okay? So over 5 cubic centimeters, yielding a density of 2 grams per cubic centimeter. Again, we measure the volume in milliliters. We realize that the milliliters is really a cubic centimeter. From that we can write it. Will it sink or float?
Float.
Will it sink or float? I heard both. I need a reason before I let you guys finish for the day.
Higher density
Kenneth.
water.
Well, it will sink because it's a higher density than water because water is 1.
Good. Water is 1. Water is 1, the density. This density is more than 1. Therefore, it will sink. Here's what I want you guys to do in the next 2 days. Listen carefully. Listen carefully, please.
Eventually my wife just quit fighting on that.
Like the first couple weeks.
My phone was dying.
This checker's wrong, man.
I was like, alright, just wait for the
They have like 2 drive-throughs.
Oh, yeah.
Damn.
You better Google it.
I don't know that. Danae's out and Mark's out.
Oh, Danae left.
Physics, yeah, physics would be Danae, Mark, Brittany.
Shading. And it won't get revealed.
Is your pen there still, Rosie?
Oh,
I had 6 the last 2 days, and I tried to get caught up, and I couldn't miss school, so.
Oh, you sure? Byron.
I always say remind you.
Have a good day, sir. Yes. Can you ask a favor? Sure.
Number 1, can I put my paper after 5 minutes?
Can you print it? Like where?
I don't know. Like, whatever computer's connected, put my paper.
Okay, it's a library or something?
Yeah. The second one, I was late for, I had problems in the morning. And I didn't do my history test.
Didn't do it?
And that's my first period. Take it.
If you want to go from 3:30 until like 4:15, then come at 4:15. That's fine, but no later than that. Because what we're gonna do today, we're gonna continue after school. So I don't want you to miss that. So if you want to go for the first 45, but after that, it's up to you to figure out. Okay? Remember? One was late. See, who took the social studies test today? The Jasmine missed.
I did.
How long was it?
30 minutes.
Oh, there you go. Be on time.
50.
It's doable.
So Jasmine, 3:30 to 4, come right after. Take a few minutes.
Mine, 3:30, there's people running around there.
I know, that's what I'm saying. Take a few minutes.
Yeah, if you
get yourself
study,
there,
that test was ridiculous.
But please don't, wait till 3:45. Go as soon as you're ready. Get him set up. And you know what you can do if you want to make it easy. If you want to take it in here, if he's not ready right after school, you can take it in here after school. I'll just get it from him. Just so you're ready in the room, so it's easier for you. All right. Wow. Next one. Let's go. Very cool. I like it.
With a word kind of like off.
Oh, let's stop recording for this yet?
I don't know yet.
Let's take a look. Look.